Today, I will be demonstrating the electroplating of copper on aluminum. I will need goggles, 100 milliliters of 2 molar copper nitrate trihydrate solution with 10 milliliters of 0.5 molar hydrochloric acid added to improve its conductivity, some copper wire to use as the anode, a piece of aluminum foil that I will be plating copper on, which will act as a cathode, and finally, an external power source to ensure that electrolysis will occur. So here's the copper nitrate trihydrate solution with HCl, the copper wire that we will be using, and the aluminum foil. As you can see, it weighs around 0.24 grams. So we've connected a power source to the electrolytic cell. The positive charge, which runs through the red wire, is connected to the anode, which is the copper, and the negative charge, which runs through the black wire, is connected to the cathode, which is the aluminum foil. It's really important to not have the clips on the wire touch each other because that would short circuit the power source. We have dialed it to around 0.5 volts and the current is 0.21 amps. I have started the clock and it will be electroplating for an hour. Here's a clear depiction of what's in the electrolytic cell. As you can see, the electrons will be transferred from the anode, which is the copper, to the cathode, which is the aluminum. So basically, when the power source is turned on, reduction will occur at the cathode. Since the standard reduction potential of copper 2+, which is positive 0.34 volts, is higher than that of water, which is negative 0.83 volts, this means that the copper 2+ ion will be getting reduced to copper metal. Meanwhile, at the anode, since copper 2+ ion and nitrate ion cannot be further oxidized, only copper metal and water can be readily oxidized. Since the standard reduction potential of the copper metal is positive 0.34 volts, as I've mentioned before, this is less than the potential value of the oxidation of water, which is positive 1.23 volts. This means that copper metal will be getting oxidized to copper 2+ ions at the anode, which then replenishes the amount of ions in the solution. The overall reaction then plates the aluminum electrode with a layer of copper. And here's the calculation for the amount of copper that will be electroplated in an hour. Since the current increased throughout this time period, we will be using 0.23 amps as the current. Since 1 coulomb equals 1 amp times 1 second, we have to convert an hour to 3,600 seconds. By using Faraday's constant as a conversion factor from coulombs to moles of electrons that will be plated, we can predict the amount of copper that will form. As you can see, we predict that 0.296 grams of copper will be electroplated. So after an hour, you can see that there's a copper tint on the aluminum. We have cut off the power source around 10 seconds early to account for the time between initially setting up the cell and starting the timer. So yep, there's definitely copper on the aluminum. After drying off the aluminum sheet and weighing it, we can see that the mass increased. The change is around 0.244 grams. Our experimental error is 17.5%. The difference between our calculated and our experimental weight could be due to some electroplated copper not sticking to the aluminum foil, which caused it to peel off after it was dried. At the same time, the change of current during the 1 hour period will cause it to slightly differ from the predicted results.